Hello dear viewers and listeners. From the previous video we know that the development of quantum theory began with the discovery of photons made by Max Planck and Albert Einstein. It has been found that light can behave either as an electromagnetic wave or as a flow of particles. Now we will continue this story. In 1924, Louis de Broglie came to the conclusion that not only light exhibits such a quantum wave duality. On the contrary, electrons and other small mass particles exhibit the properties of waves. The corresponding wavelength is inversely proportional to the velocity and mass of the particle. De Broglie waves explained in a surprisingly simple and intuitively understandable way the quantization of orbits in the Bohr atomic model, which we have introduced in the previous video. An integer number of de Broglie wavelengths must fit in the Bohr orbit. In such a case, the end and beginning of the wave coincide after the wave passes through a circular Bohr orbit, and thus the wave repeats itself. Pay attention that our two red curves are not wavy trajectories. The electron moves in a straight line in the top picture and in a smooth circular orbit in the bottom picture. The wavy red curves notate that a certain parameter becomes larger, smaller as the particle moves. Unfortunately, after a short time it became clear that the simple and understandable idea of searchable waves was wrong. But in general, de Broglie's hypothesis was extremely fruitful. It formed the ground for new quantum theory based on the Schrödinger equation and for so-called old quantum theory as well. In several subsequent videos we will talk about old quantum theory, which is also called as quasi-classical or Bohr-Sommerfeld approximation. But now we will discuss the Schrödinger equation. It was well known in 1924 that all periodic wave processes arise in theoretical calculations as solutions of so-called second-order differential equations. On the other hand, these equations are derived from the fundamental physical laws. For example, differential equations for harmonic spring motion or vibrations of a guitar string are both derived from the law of elasticity and Newton's laws of motion. Thus, there was a need to derive the differential equation for de Broglie waves, but there was a problem. Suitable fundamental laws were not known. It was not even known what actually oscillates in these waves related to atomic particles. Louis de Broglie ended his work with just amazing words. I have left the definitions of waves deliberately vague. The present theory is therefore to be considered rather tentative as physics and not an established doctrine. But fortune favors the brave. Erwin Schrödinger was not afraid to do things differently. Instead of searching for fundamental laws, he began to search for a differential equation whose solution would have de Broglie form for a free particle and would give energy levels in the case of hydrogen. Of course, it was more an alchemy based on intuition than a traditional approach generally accepted in theoretical work in physics in those days. Fortunately, the set of possible equations was small, and the promising candidate was quickly and easily detected. But it was very difficult to get solutions to this equation. Here, Schrödinger was lucky again. The strongest mathematicians of his time, Weil and Hilbert, supported and advised Erwin Schrödinger in his work. In a short time, both the equation and its solution were found. Erwin Schrödinger presented his newly found equation to scientific society in 1925 and published 4 articles in 1926. Pay attention to the common name of his articles: quantization as an eigenvalue problem. Eigenvalues are the values at which an equation has a solution that satisfies some boundary conditions. In the case of the hydrogen atom, the boundary condition is tending the wave function psi to 0 at infinity. Erwin Schrödinger said, "Look how interesting it is. My equation has a solution for such eigenvalues of the parameter E that correspond to the levels of the total energy of the electron in the hydrogen atom." It was a roaring success. The equation explained the structure of electron energy levels in the hydrogen atom and even much more. It described the de Broglie wave for a free electron, but there was a minor wrinkle in that Schrödinger added a bit more alchemy and wrote the time-dependent equation for free particles, in which an imaginary unit I appeared. The imaginary unit meant that the wave function is in reality a so-called complex function, that is, It consists of two functions in the general case. Newly opened equation also explains the periodic table of elements in chemistry. It is a little funny, but Schrödinger's equation also disproved the existence of circular de Broglie waves that we talked about earlier, and which were the main arguments in favor of the correctness of the whole de Broglie hypothesis. Now we'll see what the solution to the equation for the hydrogen atom looks like. As we have noted, the eigenvalues of the equation are the energy levels. They can have discrete values En that are numbered and that are calculated using the integers 1, 2, 3, and so on. These numbers are called principal quantum numbers. Why principal? Because there are two more sets of quantum numbers, L and M, which are called azimuthal and magnetic quantum numbers. They define and number two more characteristics of the electron, so-called angular momentum and its projection. Each set of quantum numbers n, l, and m corresponds to only one wave function psi of unique specific form in space. Analytical expressions for wave functions are extremely complex. Therefore, various types of drawings are used to demonstrate them. For example, values of squared wave functions, psi squared, can be depicted as clouds of dots. The larger the value of the function at some point in three-dimensional space, the more dots are penciled in this place. The resulting shapes are often called electron clouds. On the slide, we see several clouds of different types. At the top, we use notations for wave functions in terms of quantum numbers. They are written in purple. Notations used in spectroscopy and chemistry are written in black at the bottom. Note that the size of the clouds is much larger than the size of the electron. The electron looks like a dot in each cloud. For each value of quantum number n, there is only one eigenvalue of energy En minus Rydberg divided by n squared. But at the same time, for each n, we have n squared number of electron clouds of different types with different values of L and M. Electron clouds with the same quantum number n form so-called shells in multi-electron atoms other than hydrogen. And now we move on to chemistry and the periodic table of elements. The periodic table was discovered by Dmitry Mendeleev. A long time ago, back in 1869, he noticed that chemical elements with similar properties could be combined into groups. For 60 years, his table was used but had no theoretical explanation. Quantum numbers and electron clouds led to understanding. In 1925, Wolfgang Pauli formulated his famous principle: a quantum system cannot contain two electrons with the same set of quantum numbers. In addition to the three quantum numbers came from the Schrödinger equation, he used a fourth, the so-called spin magnetic quantum number, describing own angular momentum of the electron. Thus, the periodicity of chemical elements was explained by the sequence of peeling electron shells in multi-electron atoms. The success of the new quantum theory was just magnificent, but one question remained unanswered. What are the electron clouds consist of? In 1926, Max Born answered this question. He said that the product of the volume occupied by some small element delta V in space by the square of the wave function at a point inside this element is proportional to the probability of finding the electron inside this element. In scientific language, the squared wave function determines the probability density of finding an electron at a given point in space. In everyday language, we may simply say that the electron cloud consists of probabilities. You cannot even imagine how unusual this statement is for physics. The deal is that probability is purely theoretical substance. It doesn't exist in nature around us. It exists only in our heads on paper, or in recent years, perhaps in the form of computer code and programs. A simple example. After examining the coin in my hands, I can guess that when tossed it will come up heads about half the time, but I cannot measure this probability either with a ruler or with a watch or with any other device. I can also flip a coin, say 100 times, and if it comes up heads, say 55 times out of 100, then I can also estimate the probability as 50%, despite the fact that observed frequency was equal to 55%. Based on the above guess or observations, I can put the probability equal to 50% in my further theoretical calculations, if any. However, let's return to electron clouds. These are clouds of probabilities, but probability is the purely theoretical quantity, and the electron knows nothing about our quantum theory. Then what makes him obey the theory? Who flips a coin for the electron? Or is there no coin, but there is a law that we do not know? Or is there both a law and a coin? This remains the greatest mystery to the present day.